Okay, so I'm going to move on to the next part here, which is to recall and solve problems using the relation HF equals E1 minus E2. So I'm going to take you through this sort of on paper by showing you some notes and doing some questions as well. If I move further down here, we are in the area of finding the energy of photons from atomic energy level diagrams, and part of that is going to be conversion of electron volts to joules and back as a unit of energy. We're also going to recognise the number of possible energy changes for an electron within an atom, and we're going to recognise from the arrows whether energy has been emitted or absorbed from an energy level diagram, which is about the direction of the arrows. And we'll do a little on the finding the maximum and minimum frequency of wavelengths of photons emitted or absorbed by electrons from an energy level diagram. Sorry, there's a typo there, it should be an. Okay, so I'm going to bring you to part of the worksheet I've given already, which is this here. Okay, I'm going to point out some things on this diagram. So this here, that is the spectra itself. So I can see that with my own eyes. This is a real thing with lights, whereas this is an energy level diagram, and it is representing for me the energy levels within the electrons, and it allows me at times with values to work out some calculations as well. So this particular one is showing dropping of energy levels. So the electron existed in this case on n equals 4, and it went down to n equals 1. And since it's dropping energy levels, it is emitting a line. The arrow is going downwards. So when there is energy emitting, that arrow will be going downwards. If, on the other hand, it's an absorption spectrum, I might have an arrow like this one going upwards, because the energy level of the electron was down here, and then it was raised up here. It has absorbed an electron to do that. So we have to know that from seeing them. This is the ground level. Remember, this is the lowest energy level that it can possibly have, and this one here is the highest that's on this diagram. There may be more, but we don't go into that all that much on this syllabus, I've found. So taking a look, there are a number of lines that can be produced. We've got 1, 2, 3 produced here. But I can also see that I can have this one going down like that. I can also have this one going down like that. I can also have, is there any others? Let's have a look. 1, 2, you may be able to spot another one. 3, and then of course we've got the ones going all the way down to the bottom as well. So we've got that going all the way down to here. We've got this one going all the way down to here, like that. We've also got this one going all the way down. So there's a number of different ones, and each one will produce a line, which is why there's some of these here. Okay. Now, what we have on here is just a recognition of the different energy levels, but they might have a value written on them, and that value could be written either in joules or it could be written in electron volts. So, for example, we've got a question that we're going to do where we've got minus 21.80 here, and we've got minus 5.45, and the numbers are always negative, and these we have to watch out carefully what it says. These ones are on a scale. At the top it will say times 10 to the minus 19 joules. So these ones happen to be in joules. You have to read this scale carefully, because sometimes it will be whole numbers written in electron volts. So just as a quick reminder, converting to electron volts. So converting probably would go the other way, but converting joules to electron volts is for me to take the number, so let's take minus 21.80 times 10 to the minus 19, for example, and then we're going to divide it by the charge, the elementary charge, And so I can work that out in electron volts. Let's do that. So we've got 21.8 times 10 to the minus 19 divided by 1.6 times 10 to the minus 19 equals 13.625 electron volts. But the likelihood is that we're actually going to go the other way around. So we'll have an amount of electron volts. Let's say we've got an amount of electron volts. We're going to multiply, we multiply by E. So the previous one was divide by E. So if I had, let's say, 10 electron volts, I would have 10 times 1.6 times 10 to the minus 19 equals, that's an easy one of course, but let's do it anyway, times 0.6 times 10 to the minus 19 equals 1.6 times 10 to the minus 18 joules. So that's that conversion. Okay, now then, we are going to look at an energy change between 2 points, and we're going to show what we can do with that. So the equation, as I said before, is this. We are finding let's make sure you can see it all. Finding the frequency of a photon from a energy level diagram. Okay, so we're going to use this. HF equals E1 minus E2. So this is where you started, or where it started. This is where it finished. Okay, so I'm going to look at what photon I would get from changing between these two energy levels. So I'm going to do this one because I've got the numbers right there. Okay, so I have an electron that started at n equals 1 and ended up at ground. So it started at minus 5.45 times 10 to the minus 19 joules, and it finished at 21.80. So I'm going to get another piece of paper here to show that. I'll just cover this over so you can still see the diagram. So I'm going HF equals E1 minus E2, and I'm doing between n equals 1 and ground. So I can say HF equals minus 5.5445 minus 21.80, and that's all times 10 to the minus 19. So I'm not going to, now I can see what that sum is literally that, but what am I really finding? I'm just finding the difference between the two, so actually I can just do 21.8 minus 5.45 equals this 16.35, and that is times 10 to the minus 19 joules. Now, if I want to now work that out as a frequency, equals, I'm going to divide it through by Planck's constant. So remember Planck's constant is 6.63 times 10 to the minus 34. It's going to be a large number, but then it's light, isn't it? So I'm expecting in the hundreds of nanometers. So let's do this properly then. So here we go, I'll do the calculation now. So I've got 16.35 times 10 to the minus 19 close brackets divided by, I'll use brackets here just to be sure, because I hate having to do it again if I mess up my syntax, minus 34 close brackets equals, okay, so this is rather a large number. It would mean actually that it's not visible light, but that's okay. It is quite a large difference in numbers, so 2.46 times 10 to the 15, and it's a frequency, so it's hertz. Now I can instantly turn that into a wavelength if I want to, because V equals F lambda, and V is the speed of light, V equals C. So I can do lambda equals V over F equals, in this case, 3 times 10 to the 8 divided by 2.46 times 10 to the 15 equals, and that should give me a wavelength. Have I got that right? Let's just take a quick look. Okay. So, etc. So another thing that I can do is, if I get wavelengths instead, I can have this, instead of having HF equals E1 minus E2, it could be HC over lambda equals E1 minus E2. And then I can work out lambda instead. So first key things to look out for with any of these questions is probably that it may be written in electronvolts and it may be written in joules, so do be careful of that. I think you're probably ready to look at the questions in page 475, to which are questions 14 to 16. So have a go at page 475, questions 14 to 16. So have a go at those.